In this DeBacco University video, I'm going to be covering the magnetic properties of matter. Alright, so magnetic properties of elements are closely tied to their electron configurations. This is especially important in the presence or absence of unpaired electrons. So knowing your electron configurations and understanding your orbital notations can be important for predicting magnetic properties of elements. Now, those paired electrons in diamagnetism, paired electrons occupy the same orbital with opposite spins per Pauli exclusion principle. These essentially cancel out. So we need one up arrow and we had one down arrow. And this cancels out their magnetic moments. No magnetic moment essentially means diamagnetic behavior. You have a very stable, low degree of magnetism here because essentially you've got opposite spins canceling each other out. So we have this diamagnetism present. Now those unpaired electrons, those occupy orbitals singly, each with a spin that generates a small magnetic moment. Unpaired electrons have uncanceled spins, creating a net magnetic moment that aligns with an external magnetic field. The more unpaired electrons, essentially, the stronger the paramagnetic effect. Because now instead of having this canceling, now you're getting electrons starting to spin in the same direction. Because we always start with one electron per box, we're doing our orbital notations, we have all those electrons spinning in that same direction. And that can start to increase the strength of magnetism while decreasing the stability chemically a little bit. So again, here's our paramagnetism. Moments align weakly and temporarily, producing a mild attraction and disappears when a magnetic field is removed. Ferromagnetism, unpaired electrons in specific materials align strongly with magnetic domains, producing a powerful, persistent magnetic effect. So again, both of these are stronger than our diamagnetic, but ferromagnetic is by far the strongest of the three we're comparing here. Now those transition metals in magnetism, transition metals are elements with partially filled D or F subgroups, or sublevels, in the groups 3 through 12 in the periodic table. Their electron configurations often include unpaired electrons in d orbitals, making them key players in magnetism. And visually we can see that right here. We see a lot of arrows going in one direction without a lot of cancellation occurring. This makes many transition metal ions paramagnetic or even ferromagnetic depending on the electron alignment. And we could see that here with a lot of single arrows because we've got a lot of those D has a lot of electrons potentially to fill. And if we just have one electron filling those, we're getting all those electrons spinning in that same direction. Now, transition metals in magnetism, well, most transition metals are paramagnetic due to the unpaired d electrons with the strength of paramagnetism depending on the number of unpaired electrons. A few transition metals, notably iron, cobalt, and nickel, exhibit the ferromagnetism because their unpaired d electrons can align in magnetic domains within their crystal lattice structure, that's the physical orientation of the atoms, producing strong permanent magnetism. So these iron, cobalt, and nickel I've highlighted here, these are the ones that can have the strongest degree of magnetism. These are the ones that are going to exhibit that ferromagnetism. Now those paired and unpaired electrons, just to give a little visual here, remember paired electrons cancel out magnetic moments, leading to a diamagnetism, which is a weak repulsion, stable configurations like a full outer shell or a full sublevel. Those unpaired electrons create magnetic moments causing paramagnetism, which is a weak attraction, or ferromagnetism, which is a strong permanent magnetism in specific cases, as we saw there with iron for a key example. When we talk about those electron pairs, again, we're talking about those single arrows, not having those doubly filled up and down arrows where they're kind of canceling each other out. Now those magnetic properties of those transition metals, they dominate magnetism due to the d orbitals, which often have unpaired electrons. Ferromagnetism is rare and requires both unpaired d electrons and a suitable crystalline structure, such as iron, cobalt, and nickel. Stability link paired electrons, such as full sublevels, enhance chemical stability, but at the same time eliminate magnetism. So you kind of have that inverse relationship. Unpaired electrons have full or no special arrangement. They basically reduce the chemical stability but enable magnetic properties. So you really can't have both. Lastly here, how would you predict magnetic properties? Well, you want to write down the electron configuration, then draw the orbital notation, which remembers the boxes with the arrows, count the unpaired electrons. If you have no unpaired electrons, the element you're probably looking at is diamagnetic. If there's one or more, it's probably paramagnetic, and if it aligns domains, then you're looking at the special case of the strong magnetism called ferromagnetic. So we can work through some examples here, go through the importance of knowing your electron configurations as well as your orbital notations, because it all gives you the ability to predict an element's magnetic properties.